Good morning. It's really a pleasure to be with you today. I think it's the fourth time I'm coming to this forum, and each time I've enjoyed it a lot. So my name is Jean-Noël THÉPAUT. I'm the former director of Copernicus Services at ECMWF, and now I'm a sort of freelance consultant for ECMWF and also the World Meteorological Organization. And today, we will speak with my colleague Christina KÖPKEN-WATTS, who is sitting now and will speak after me about the contribution of satellites to weather forecasting skill. So you get two speakers for the price of one. Let me move to the next one. So first of all, so let's go back to weather and what is numerical weather prediction in a nutshell. So you as a sort of journalist and TV speakers, you are at the end of the food chain. This is the umbrella and the lady taking the umbrella. But to do that, we need observations. We mix these observations with numerical models to have initial conditions on a grid over the Earth, and then we have models to forecast the weather. So how do we do this? By pressing the button. Oh, yeah. Yeah. So how do we capture the weather? So to predict the future, we need to know what the weather is today. So we need to observe the present. So every day at the European Weather Center, where I'm coming from, ECMWF, we assimilate about 800 million daily observations. We have a lot of things to observe before predicting it. It's not only wind, temperature, as perhaps it was 40 years ago, but we have to really estimate the state of the planet at a given time. So it means we need precipitation. We need also things that already Pierre-Yves and Mark, to some extent, talked about, so sea ice, waves, because we are in a coupled world. So all of this needs to be done accurately before we can even think about doing a forecast. So I want to do justice to in-situ observations. I know we are in a satellite arena here today, and we will talk about satellites a lot over the next 2 days. But in-situ observations, what we call conventional observations, are very important, and it's a snapshot of what observations from aircraft, from buoys, from in-situ ground observations, radio sondes, etc., get into the system. And in terms of satellites, of course, over the last 30 years, we've increased greatly the use of satellite information into the system. This is a graph showing the evolution of the number of instruments, satellite instruments, that are ingested in the ECMWF system. And you can see that originally, the US was mainly providing the observations that we needed for numerical weather prediction, but progressively, and in particular with the growth of EUMETSAT, the balance is much better now, and we have a real strength in Europe in terms of meteorological observations for numerical weather predictions. This is a slide that my colleague Alain gave me for this presentation, and I think it's a very nice visual representation of the two big classes of satellites that we are assimilating in NWP. On the left, you have the geostationary satellites, which rotate at the same speed as the Earth, so they observe always the same thing, and they are at 36,000 kilometers or so. And you get a picture of the atmosphere every 5 or 10 or half an hour, all the time. And this is extremely important for nowcasting applications and also short-range prediction. But you also have the polar system, so satellites flying at around 800 kilometers and going through the pole. And there was a nice movie from Mark earlier on. And this is very important for numerical weather prediction at medium to long range, because it's a global coverage, and it provides a full picture of what we need to initialize the models. So this is what we ingest. This is a snapshot of 6 hours of data that we ingest in numerical weather forecasts. So you have the sort of tracks of the polar satellites, the geostationary ones. And on the top right here, you also have what we call the GPS radio occultation data. Because if you have sensors, GPS sensors on satellites, you can also track the GPS signals, and that gives indirect information on temperature and water vapor, which is extremely useful for numerical weather prediction as well. A prerequisite to assimilate observations in numerical weather models is that observations need to be able to, the models need to represent accurately the observations. Observations are here to correct the model before the forecast. But if the model is not able to make sense of this observation, then the model will go back to its climatology or to its biases. So it's very important that models are up to represent observations so that these observations can be assimilated properly. And that's very important. And over the past decades, the quality of the models has improved to an extent that was perhaps not even envisaged 20 years back. And that really allows to exploit observations in a much more efficient way. And this is a comparison of a model, a forecast, 18-hour forecast from the operational model of ECMWF with an image, a gauze image over America. And you hardly can tell which is the image and which is the model. You can, if you have an accurate eye, because if you look at the stratocumulus in west of South America, you can see that the granularity is not exactly the same and it's still a bit gross. But giving you a hint of what we are going towards, in particular with a project that perhaps we will talk during the panel, which is called Destination Earth, we will be able to provide simulations at very high resolution. And here you can see that, for example, for the stratocumulus, which is very important also in terms of radiation budget, the representation is becoming extremely good, and the representation of cyclones as well. So it goes hand to hand. Progresses in models and progresses in observations go really hand to hand. So data simulation, which you heard about, is really putting the observations together to initialize the model and reducing the error in the forecast. So at the moment, in most of the centers, we have an ensemble of forecasts, which gives you an idea of the uncertainty. So that gives you the ability to say, well, it will rain with a probability of 3 to 5 or something like that. Underneath, there is an ensemble of forecasts to be able to get this uncertainty definition. And observations manage to reduce this uncertainty, and then you carry on like this. And on the right panel, you have the impact of observations. So it's a metric that I'm not going to detail, but it allows to provide an idea of which observations matter most in terms of reducing the forecast error. And you can see that satellites are really becoming very important: microwave water vapor, microwave temperature, infrared temperature, etc., etc. But you still have a few significant impact from aircraft, for example, or sounding instruments or in situ instruments. But the satellites are really giving the most of the impact nowadays. And this is an example. So a typical example to validate the impact of satellites on the forecast. This is a case where you do a forecast with all the satellites you have at hand, and then you do another experiment when you remove all the satellites, and then you see what happens. And this is a case of a cyclone in 2017, where you see that the formation of the cyclone is almost inexistent if you don't have satellites in your system, and you miss completely the trajectory of the cyclone. So that's a nice illustration of the impact of satellites in weather forecasting. This is a sort of an iconic plot for at least people in numerical weather prediction, but I think it has also gone a bit further. And it shows the quiet revolution of numerical weather prediction with the increase of skill with time, starting from the 1980s to today. This plot is from yesterday, actually, it's updated every day. And it shows the quality of the forecast at different range, day 3, day 5, day 7, etc., etc. Thick line is northern hemisphere and thin line is southern hemisphere. And what you can see here is that it has improved and it is still improving, although it's becoming difficult to pin it down, but it's still improving. But what I would like to draw your attention to is what happened in the late 90s, beginning of 2000, where the scores in the southern hemisphere, so the quality of the forecast in the southern hemispheres, started to equal what we had in the northern hemisphere. And before that, it was not possible because we had less observations and we were not able to use satellite observation in a satisfactory way. While with progresses in models, in data simulation, by the 2000s and onwards, now we are able to, thanks to the progress we did in exploiting satellite data, we are able to have similar scores in both hemispheres. And I will finish by saying a few words about climate monitoring, although there is a full day tomorrow about climate, so you will hear much more about this. But satellite observations and observations in general are also very important to be ingested into what we call reanalysis, which is replaying the past and present climate. So we have a reanalysis at ECMWF under the Copernicus program, which is going back to 1940 until today, real time. And this allows to put the anomalies that we see in summer or in winter in a wider context by looking at what was the climate in the past. But to do this, there is a lot of work being done in reprocessing observations, old observations, including satellite data, to be able to have a fine description of what the climate was in the past decades. And the next slide shows on the left, this is something that you can't read probably, but each little line corresponds to a satellite which has flown for a while and which has been reprocessed so that we can exploit information from the satellite, which we couldn't do at the time it was flying. So there is a second life or maybe a third life for all these satellites that we can really exploit now with modern methods, with better model, and that allows to look at the climate over the past decades. And thanks to this, we can provide information like monthly bulletins. I think Osden is a big fan of this one because we see you on TV presenting this, and the annual state of the climate that we do with the WMO. And underpinning this is the reanalysis that I'm talking about with a lot of work. And we need to be scientifically watertight because there is enough suspicion of being alarmist. So we need to be absolutely confident into what we are providing you to communicate on. And now, enough for me. From global to regional, Christina will take over and walk you through the rest.
Okay, so now we'll have a look at a few more examples how satellite data are used along the forecasting value chain. And I'll start by illustrating a bit what I mean with forecasting value chain. So first, the data enter, as Jean-Noël has described, our global model system. And nowadays, it's about 85% coming from satellites. The remaining is, of course, also a very vital source. And then nested into this is a smaller area with a higher resolution. And both the model as well as the satellite data then flow right into the forecaster's room, where our forecasters observe the current weather evolution, and their role is increasingly important to provide warnings and advice in everyday and especially in extreme weather situations. And they've got a range of information available at their hands, models, radar, all sorts of observations, and of course the big satellite screen. Likewise, the data feed through into publicly accessible means, for example, a mobile app where forecasts and also warnings are available. And we've got a large range of user-specific products. They range from shipping forecasts, agriculture, to, for example, aircrafts. And all the products we provide integrate a variety of data. Satellites play a key role, merged with other observations and models. Now, just to pick one example, this is a nowcasting product for aviation. And this is the main input is geostationary satellite data. As an illustration, top left, you see we pick a few channels which provide essential information on clouds, combine this with model information on atmospheric stability, so ability to provide convection, and as well lightning information. This is a ground-based system. And then a very fast algorithm provides green, light, moderate, and severe, basically different color schemes as convection information. And in future, of course, lightning information also from satellites, the new instruments can provide very important additional data. So now how is this forecasting data used, or this nowcasting product? It gets basically wound up for different specific platforms intended for aircrafts and relayed through our servers, basically online into the cockpit. You see there on the right-hand side, the warning product, on the left-hand side, the radar. And the nice thing is then with the radar, you only see the current information. Our product also provides some extrapolation in the future using satellite-derived winds. And additionally, there's also cloud height top product, but this is more used for flight route planning ahead of the flights. Now moving into a second example, the nowcasting does not last for a long range, so we need to combine this with models. Just to illustrate how this works, imagine we've got some verification score, be it thunderstorm position or intensity, rain intensity. The nowcasting is very close to reality because it starts from the observations, whilst the NWP forecast, we have to start a little bit ahead of time, is not as close initially, but then overtakes in quality at a certain stage. And what we're working on intensively in a big project is to both improve the nowcasting and the NWP to get closer to the observations at the start, to then provide blended combined products of good quality. And the current crossover time is roughly at 1.5 hours. So on the nowcasting side, we work a lot on radar data, improving the methods, getting more probability information into the system. And on the NWP side, we have now very rapid update cycles to take observations in. We issue hourly forecasts at high resolution, 2 kilometers, moving to 1 kilometer or even further. And they are really focusing on the short range up to 12 hours. And the models are especially provide additional parameterizations or the way they're programmed to represent cloud processes more accurately. And we use more data, radar, but what I want to speak here a bit more is the satellite information, and there's also lightning that we are integrating. And I'll now show an example of what we do with the satellites in this context. So we have from Meteosat, the geostationary satellite over Europe, really good cloud information. And up to now, not everything was used, but we've been working over the last years to include especially the visible information with a forward operator or a simulation possibility so that we can see how the model would see the convection. And we aim at the direct exploitation of cloud information, which so far has not always been done in the assimilation side. So just to illustrate, from the convective situation, the channel in the visible and moisture channels pick very nicely the thick clouds. If we look at the low clouds, it's only there in the left-hand corner, visible in the visible channel, very fittingly. And the way we do that now, when we use the data, we evaluate, does it really help over a longer time? For example, 1.5 months, we run this. And this illustrates in green, the relative improvement we get in the forecasts over the forecast range, here displayed 0 to 13 hours of forecasts. And we see using this visible information helps cloud cover, radiation to meter temperature, which is of course not only for large scale planning, but for individual planning at building or private level. There's a very nice tool which takes this radiation into account, which is available, open to everyone, supported by the European Commission, where you can just pick a location. And here for fun, I put in the HumanSat building, and you put in your PV panel details and panel orientation, and then it provides you straight away with an output, how much power you can expect along the course of the year, here from January to December, variability expected, etc. So this is just to say also, we talked about climate change affecting us. This is partly supporting the solutions that we've got at hand. And of course, future satellites will help at making this better. Just one example, there are of course many areas where the future satellites help. This is the product at a count resolution, this radiation I was describing. And in the future, when we'll have now much higher resolution data, we can have much more granular horizontal information, which is of course beneficial. So to summarize, satellite observations are key inputs to our forecasts. We are using them increasingly well and with complex methods. Also, artificial intelligence goes in here now increasingly, more areas and conditions. They measure a wide range of products and parameters, also trace gases, lots of things we haven't talked about here now. They feed directly into nowcasting and warning products for a really large range of users. They support climate monitoring and the transition to renewables. And we're looking forward to more satellites that further increase the potential across the whole range of applications. And I hope I wasn't too fast now, but time was pressing.
Thank you, Christina. Thank you.